Welcome everyone. We are going to talk about the conference paper which we are following for our final year project, AI-driven MDT footprint prediction. So let's start with this important paper from 2020 called Enhanced MDT-based Performance Estimation for AI-driven Optimization in Future Cellular Networks. It was written by researchers from the University of Oklahoma and Qatar University, and it was published in IEEE Access Volume 8 in September 2020. Their work tackles some big challenges in how we measure cellular network coverage using MDT, which is exactly what our final year project is about. Now let's move on to the next slide. Here we are talking about the motivation and relevance of this paper. Well, when network use MDT data from phones to map coverage, they face three main problems. First, location data isn't always accurate. Second, diving areas into bins causes errors. Third, in busy networks, we often don't have enough data points. These issues make it hard to automate network improvements. So our project takes their work further by using AI to predict coverage more accurately, even when the data is limited or noisy. In the next slide, we are discussing the key contributions of this conference paper. This paper made three big contributions. It was first a study how all these areas work together, and it found the perfect bin size to minimize mistakes. And also, it showed how to fix coverage estimates in real networks. According to the latest data, this work has been cited 24 times by other researchers and also published in 6 different versions and also ranked as the top search result for MDT optimization studies. This shows it's become a key reference in the field for our final year project. We are using their methods as the foundation for our AI approach, especially building on their error analysis framework to make coverage predictions even more accurate. Thank you.
Let's explore the core research problem addressed in this paper. The modern cellular networks need fast and intelligent ways to estimate coverage. Instead of expensive drive test, operators now use a feature called MDT in long form minimization of drive tests, which collect signal measurements from different user equipments. While this technique is cost effective and scalable, it comes with three major challenges. So let's see what are these challenges. First, there is the positioning error. That means the location reported by the user equipment, typically using GPS, can be inaccurate in most of the times. This means signal strength readings like RSRP get mapped to the wrong place on the coverage map. Let's see about the quantization error. To simplify data handling, the coverage area is divided into bins and all user equipments within that bin are averaged. But this average lead to a loss of precisions because because especially in the areas with a lot of signal variability, it doesn't work. And the final one is sparse user reports. In small cell deployments, there may be only few active users in any given time. This leads to empty or undersampled bins, resulting in unreliable or even missing data in many parts of the network. When we discuss about the previous research, most previous researchers looked at these problems in isolation or in pairs. That means they have not addressed these three problems simultaneously. What makes this paper unique is that this is the first research to jointly model all three. By doing so, the authors were able to uncover important trade-off between these errors and propose new optimization strategies to improve coverage estimation accuracy. So when we go to the next slide, we have methodology. We have addressed the methodology of these papers. So uh, the authors they began by creating realistic 3D simulations of a cellular network using actual terrain, building heights, and clutter data to model urban conditions accurately. User devices were placed using a Poisson distribution to mimic real-world traffic patterns. To simulate this positioning error, each reported user location was randomly offset by a distance between 0 and 100 meters. They also varied bin widths from 0 to 50 meters to observe the impact of the quantization. Uh, then next part is the error analysis. Each type of error, positioning, quantization, and data sparsity was modeled mathematically. They use logistic probability distributions and fitted curves to quantify the effect of each factor. Importantly, they didn't stop at individual analysis. They also studied the combined effect of these errors. This joint analysis revealed how changing one parameter like bin width could reduce to error but worsen another. The ultimate goal was to find an optimal bin width that would minimize the total coverage estimation error, even in the presence of both location inaccuracy and sparse data. To handle these missing data problems, they tested several recovery techniques and found that kriging or geostatistical interpolation method gave the best results in reconstructing accurate coverage maps from sparse measurements. In summary, this methodology was both practical and rigorous, combining real-world simulation with mathematical modeling to improve AI-driven coverage estimation in future networks. Thank you.
In this section, we highlight the key results and insights from the study. The research introduces analytical modeling and calibration framework to enhance accuracy of MDT-based coverage estimation. These improvements are especially crucial for enabling more reliable AI-driven optimization in modern cellular networks. The study identifies three main sources of errors in MDT-based coverage estimation. First, positioning error. Inaccuracies in user equipment's GPS data create uncertainty in location mapping. Second, data sparsity. In areas with fewer users, we lack sufficient reports, leading to poor coverage representation. And the third, quantization error. When signal data is aggregated into spatial bins, the finer details of signal strength get distorted. These errors are not isolated, they interact, making it important to address them jointly. To reduce the total estimation error, the paper proposes a mathematical framework for selecting the optimal bin width. This bin width is based on two main factors: standard deviation of the use equipment's positioning error and the density of MDT reports in the area. The result is a bin size that strikes a balance, reducing sparsity and quantization errors, while also minimizing the impact of inaccurate user locations. This provides a more principled alternative to arbitrary or fixed size bins. Beyond bin optimization, the authors introduces a calibration framework that uses a small amount of ground truth data. This helps correct systematic biases in the coverage map, especially in areas where MDT data is sparse. When combined with optimal binning, this calibration process leads to 30 to 40% reduction in estimation error in simulations. It also reduces the reliance on expensive and time-consuming drive tests. To summarize, the main sources of estimation error, positioning, sparsity, and binning, must be addressed together. The proposed framework enables mathematically guided bin sizing adaptable to any network scenario. A lightweight calibration step using minimal ground truth further improves the accuracy. Overall, this approach results in more reliable coverage maps, which in support AI-based autonomous network optimization.
Let's look at how this research translates to real-world solutions. First, our framework enables truly AI-driven network optimization. Imagine a system that automatically detects coverage holes, those frustrating dead zones they all encounter, and self-heals by adjusting parameters in real time. This isn't science fiction. It's what this optimized MDT approach makes possible. For operators, this means two game-changing benefits. First, unprecedented accuracy in coverage calibration. Notice how these calibrated maps reveal problems traditional methods miss. Second, it transforms network planning. When you know exactly where weak points are, you can make smarter decisions about where to deploy small cells or boost capacity. And here's the bottom line. Early trials suggest 30 to 50 percentage reduction in drive test cost. That's millions saved while actually improving service quality, a rare win-win in telecom. Next, let's see the comparison with the prior work. You might wonder what makes this approach special. Previous studies treated positioning errors, binding issues, and sparse data as separate problems. But in reality, they interact in complex ways. Here, the first to model all three jointly, revealing critical trade-offs. For instance, that optimal bin width they kept mentioning isn't just a theoretical concept. It's a precise solution emerging from understanding how these errors influence each other. This matters because all AI models are only as good as their training data. By cleaning the MDT inputs, they're giving network AI the clear vision it needs to make better decisions, like giving glass to someone who's been squinting at blurry data for years. Next, for the last, let's see the conclusion and the future of this study on the conference paper. To wrap up, three big ideas. First, we've shown that balancing GPS, binding, and sparsity errors through the optimal bin selection creates more accurate autonomous networks. Second, this isn't just about maps. It's the foundation for the self-driving network of 5G and beyond. Looking ahead, they are excited to adapt this to mmWave's unique challenge and explore drone-assisted data collection. But the real frontier, using this insight to build predictive AI that anticipate problems before users notice them. In closing, this work bridges the gap between today's manual process and tomorrow's autonomous networks, where better data drivers, smarter decisions, hidden problems become visible, and everyone gets more reliable service.